Hello and welcome back to Computer Organization. So far we have looked into the implementation of microarchitecture, or we named it as processor design. So the way we have looked into the processor design or microarchitecture design is we have divided the whole task into 5 subtasks. So those 5 subtasks were basically instruction fetch, then operand fetch, followed by the execution, followed by memory access, and finally the register write phase. Now this implementation, this processor is complete in a way. Logically it is, or basically it can perform the functions of a processor which can deal with simple RISC instructions. Now we did incorporated some optimization in our processor design, though we have not explicitly mentioned it. I will just highlight what do I mean by optimization. So for example, one very crude way of implementing this processor would have been, like, we know that there are 21 instructions, so we can have dedicated hardware to execute those 21 instructions. For example, let us say I have an add instruction, so I can have a dedicated hardware which will, from the register file, which will take the 2 operands depending on which 2 operands I want to add. Then I can have an adder, and then the adder adds the numbers and then stores the result back into the register file. Similarly, for a subtract unit, I can do the same thing again. So I will have a dedicated register file read mechanism, and then I will do the subtract and then store the result back, and for all the other arithmetic operations. Similarly, branch instruction, I can have dedicated hardware taking care of each of these instructions. Now intuitively, as you can understand, this will be very resource hungry implementation. The overhead will be really significant, and if you think of a more complex processor where maybe the number of instructions will be much more, then your hardware will blow up very quickly. So that definitely is not the best way of implementation of your microarchitecture. Now what we have seen in our implementation that we discussed so far, we do not have dedicated hardware implementing only one instruction as such. So what we have done, we have in a way created some generic hardware. For example, we have one ALU, then we have basically this register read write mechanism, then the branch calculation mechanism. The branch, for branch calculation, we have been we also use the ALU for doing the arithmetic operations. Similarly, for compare instruction, we use ALU. For identifying the addresses for store and load, we use the same ALU. So we are, in a way, basically we are multiplexing the time multiplexing the same hardware for getting different kind of things done, whether it is address calculation, whether it is branch outcome calculation, or some arithmetic operation, we are using the same ALU. So this way we have introduced some optimization in the design, and the design is much more compact compared to a situation where each instruction will be executed by a dedicated hardware. All right, but is this good enough? Let us look into it. So if we look into the basically 5 stages which we have discussed for our processor. So those 5 stages are basically your instruction fetch, operand fetch, execute unit, and then memory and read register write. Now among these 5 stages, let us say I am dealing with one instruction and the instruction is currently in the fetch stage. Now all the other units, what are those units doing at this point? Basically they are doing nothing. So they are just waiting for the the instruction to move forward and so that they can execute. Now, when one instruction is in memory access stage, let us say, then like all the other modules or all the other sub modules are not doing anything because they do not have any work to do. You have to wait till this instruction which you have fetched currently, that goes till the end of this stage, and then only you can bring in new instruction. So, let us say for this whole task to get executed, you need t units of time. Then for every instruction you have to wait that amount of time before you can start executing the next instruction. Is there any other way? Is there any better way of execution? So, one concern here is that I have so many different modules, and these different modules are more as we have designed them, they are pretty much independent of each other. So, when I am fetching an instruction, I do not need or for example, let us say I am doing some memory access at this stage, I really do not need anything from the instruction fetch or operand fetch or execute stage, because they are fairly independent stages. Now, since they are by design very much independent, we can now think about implementing a very important concept which is called pipelining, and this is the most important concept in terms of microarchitecture that we will learn in this course. So, I want you guys to pay utmost attention, and we have already spent some significant amount of time in our initial classes to basically motivate you why pipelining, and through some analogies why pipelining makes sense. So, we will see how we can implement it in our microarchitecture. All right. So, from our discussion so far, what we have seen, that we have already designed a processor. The processor is actually functional. So, if you want to write a Verilog or VHDL code looking at the different modules and interconnect them, this will behave like a simple RISC processor. And we have also said that the processor is already incorporating some optimization in a sense that it is multiplexing many modules, so that you do not unnecessarily have dedicated hardware or redundant hardware for each of the instructions. So, you are doing multiplexing. By the way this processor or microarchitecture is designed, we have already designed the processor into 5 almost independent stages, and that will help us in incorporating pipelining. As we have discussed earlier also, intuitively the concept of pipeline says that okay, you make your whole task into multiple subtasks and make those subtasks completely independent of each other. This is very important. This subtask has to be completely independent of each other. Now, once you have ensured that, now you can basically execute different parts of different instruction in these different modules. So, for example, I have, let us say, 5 instructions. So, instruction 1 can be in the register phase, instruction 2 can be in memory access phase, 3 can be in execute, 4 can be operand fetch, and 5 can be and at instruction fetch stage. So, we will talk about it in more detail, but the key here is to remember that they has to be completely independent of each other. All right. Okay. So, now let me dive into the explanation of pipelining, and we will see the key points of pipelining. All right. So, now I guess all of you can intuitively understand why in the microarchitecture implementation we divided the microarchitecture into 5 stages, because ultimately we want to implement pipeline, and that will be useful. So, what all we will be learning? We will be starting with basics of pipelining, um, the basic framework that is required to understand the pipelining concept. All right. Okay. So, before we jump on to the designing or associating the pipeline design with our current microarchitecture, we have to understand few basic stuff. So, basic key points of an ideal pipeline. So, what is a pipeline? So, pipeline is basically you have multiple stages. Let us say stage 1, stage 2, this is 3, 4 and so on. All right. So, what we are essentially saying that one task is divided into multiple stages, just like we have discussed in our previous lecture. Now, each of these stages will get data and then do some work here and then pass this data to the next stage. Now, how do you basically ensure that the data moves to the next stage only at a particular time? Because this is very, very important. Why? Let us say I am working on instruction, let us say n, instruction number n, which is in stage 1, or let's think about it in a more generic form. Let's say that we have we are looking at a car manufacturing assembly line, and the cars are moving from one stage to another stage, and some work is getting done when that car is in that particular stage, and this car which is in this stage 1 will move to the next stage, which is stage 2, only at a particular time, after a fixed period. And what will be that period? How that period will be determined? We will come to that. But why it is important? Because let us say this stage takes 10 seconds, this stage takes 8 seconds. All right. So, it might happen that I have multiple these stages, and let us say this stage takes 11 seconds, this stage takes 9 seconds. All right. Now, what is going to happen? So, the car moves here. After 8 seconds, this car is ready, because the whatever task was supposed to be performed in stage 1 is done. Now, the car is ready to move to the next stage. But can it move to the next stage? It can't, because stage 2 is already handling another car, right? Now, this at stage 2, the task which is performed at stage 2, that requires 10 seconds. So, here this is very important, that though after 8 seconds this car is ready to move to the next stage, but this will not be able to move because this stage is not done, because you can't just pile up cars. So, one stage can hold only one car. So, I am already working on a car in stage 2 and I will need 10 seconds. So, till I am done with this 10 seconds, I will not be accommodate the next car. So though this task is done in 8 seconds, it has to wait till this stage is empty. Now when this stage will be empty? This stage, the task needs 10 seconds, that is fine, but this stage will be empty when the car can move to the next stage. Now what is the next stage? Next stage need whatever function we are doing in next stage, it requires 11 seconds, 11 nanoseconds. Now the stage 2, car in stage 2 can move to stage 3 only when this stage 3 is again done with its work and the car moves next. So you see that this is very, very important to understand that though the stage is done in 10 seconds, but it will not be able to move to stage 3 and it will wait till this stage is done and the car moves to the next stage. So this will take 11 nanosecond. So after 11 nanosecond, so assuming here that all these stages started their functions at the same time, alright. So here our assumption is that every stage has a car and in a synchronous manner they started working on that particular car in that particular stage. So after 11 seconds, 11 is the highest time that is taken by among all the stages. So stage 3 takes most of the time and it is 11 nanosecond. So after 11 nanosecond, we can basically move the cars to their subsequent stages, because after 11 nanosecond this stage will be free, so the car can move to stage 4. So stage 3 is empty, so at that time the car which is here, that can move to here, the car which is here, it can move to here, and a new car I can put in here, alright. So to understand pipelining, it is very, very important to also understand that at what point I can pass the data to the next stage. Now this is fine that we logistically or we understand that okay, since this stage will take maximum amount of time and the car will not move to the next stage, so I will not be able to pass the next cars and so on. Now how do you regulate that? Because let us say after 8 nanosecond, if there is a direct path, so this stage will say that oh, I am done, so take the car. It can push the car to the assembly line. Now how do you control that? To do the controlling, you need something called sequencing elements. What do we call it? Sequencing element. Now in our digital circuits, the examples of sequencing elements are flip-flops, alright, sometimes latches also, but we will stick to flip-flops. So what is a flip-flop? So a flip-flop is a very, very simple element where there is a input, we call it, let us say, data input, and then there is a output which is called Q. I am drawing a very simple flip-flop. There can be Q bar, and you might have read about SR flip-flop and all these things. So we are looking at only a D flip-flop where there is one input data, one output Q, and then there is a clock input, alright. And these flip-flops are edge triggered flip-flops. So let us say this is a positive edge triggered flip-flop. So what does that mean? So this means that whenever the positive edge of the clock comes, so this is the positive edge, right? So, if my clock signal looks like this, so these are my positive edge of the clock. Now, whenever this positive edge comes, whatever is the content of or whatever is connected to this data input, that value is basically captured and that value is available in Q. Okay. So, just to pictorially show this, so this is clock, let us say this is data. So, whatever value is there in data at this point, that will be captured and that will be available at the Q output. Now, again when this data will get updated? When the next clock edge comes, alright, and so on. So, Q will hold on to the value which the data had when the positive edge of the clock arrived. Now, you can think about how these sequencing elements work. So, if I have a D flip flop kind of thing here, alright, and all of them are connected to the same clock. So, what happens? Whenever the positive edge of the clock comes, D, the value which is available in the input, D input, that comes available in Q input. So, in a way, whenever the clock signal comes, the data available in stage 1 moves to stage 2 and so on, alright. So, as if this is a switch, whenever this switch is pressed, the car from the previous stage starts moving to the next stage. Now, the obvious question will be, at what frequency I will press this switch, or let us say I will at what frequency the car should move to the next phase, next stage. Now, that will be dependent on the stage which takes maximum amount of time. So, among the 4 stages we have seen here, this stage takes maximum amount of time. So, if I press this switch which allows cars to move from the previous stage to the next stage at a frequency of, let us say, at a frequency which is corresponding to 11 seconds or more. So, let us say I the time period of the clock I choose is 12 nanoseconds. So, what will happen? So, every stage is ready with their result. So, basically the D input which is available in this sequential element is proper, because I have already spent more than 11 seconds. So, the stage 3 outcome is ready, the car is ready to move to the next stage, and then I press the button which allows the car to move to the next stage. And if I keep on doing this with a period of 12 nanoseconds, then there is no problem, or 11.5 nanoseconds or 11.1 nanosecond, depending on like few other things which we will not go into right now. But essentially what we are saying, that you can design this kind of a pipeline, provided that the period at which you will move data from previous stage to the next stage is dependent on the stage which is taking maximum amount of time. I hope this makes sense. So, this is nothing but your basically in a sense it is also called RTL, register transfer logic. So, what is RTL here? So, if we basically we are interchanging between our car assembly line and actual circuit assembly line. So, here you see that if you recall, each of these stages like instruction fetch stage, operand fetch stage and all these stages, individually these stages are nothing but combinational circuits. So, what is combinational circuit? So, there is no memory, there are some gates and basically depending on the input of those gates, current status of those inputs of the gates, you get some output. Now, if you broadly look into the design, so we have design of our design of our processor. So, we have our IF stage, instruction fetch stage. So, I will just also try to show you what was there in IF stage, so that we can remember. So, this is what our IF stage looked like, right. So, this block inside the box. So, you see that there is a resistor, basically we have to read a resistor, we have to calculate the next PC, which is a addition operation, and then we have to basically supply the 32-bit instruction in this IF stage after reading it from the memory. So, if I say that okay, all these things are done in this IF stage, and once the, so what are the outputs of this IF stage? So, output is basically we get the instruction. Now, after reading it from the memory, the instruction is available and also the next PC is also calculated. So, these are the two things which are sent to the next stage. So, what is next stage? Our next stage is basically operand fetch, right. So, the input to this operand fetch is these two input, our instruction and the next PC. So, if we do not have any pipelining concept, so as we have seen in the previous thing, previous discussion, so this input will directly go, basically this output of IF stage will directly go to the operand fetch stage, and as soon as the results are ready, it will be available in operand fetch stage. Operand fetch stage will start, once the data is available, then it will start looking at the instruction. From there it will try to find out like what will be the what are the different operands, and it will give you the outcomes like this immediate value, branch target, OP1, OP2. So, these are the 4 outputs it will be giving, right, and then there is execution unit and so on. Now, it's very much similar to the car assembly example we are talking about. So, we are dealing with, let us say, one instruction. So, this one instruction we fetch, then it moves to the next operand fetch stage and then execute and so on. Now, if you want to deal with multiple instructions at a time, let us say, because one thing we also observed, that when instruction fetch stage is working, the other stages are idle. So, we do not want that, we want to exploit our these different modules parallelly, so that we get better and better performance. Now, to do that, we have to have a mechanism where multiple instructions can be in different stages. Just like in this car assembly example, one strategy can be I deal with one car at a time. So, one car comes, it moves to stage 1, then it moves to stage 2, then to stage 3 and stage 4, then it goes out. Now, you can count the number of total number of time it will take. So, you need 18 nanoseconds, 18 plus 20. So, basically 38 nanoseconds to complete this task. Now, so one car will require 38 nanosecond to pass through these 4 stages, and then only the next car can move in and so on. But since now we have said that okay, there can be multiple cars in the assembly line, so what is happening? So ideally after so if I clock it if I clock it at 12 nanosecond, so you see that every 12 nanosecond a car will be coming out of this assembly line, right? Because every 12 nanosecond a new car will be inside in the assembly line, and a new built car will come out of this assembly line. So earlier you had to wait 38 nanoseconds to get one car, and then again after 38 nanoseconds you will get the next car. Here you will get one new car every 12 nanoseconds, right? So this is much better. So similarly, if we can allow multiple instruction to be in different stages of execution, then we will be able to execute much more instruction than what we can otherwise. So one key point here is that you see that these stages are very independent. So the stage 2 is not at all related to any other stage. So if it is, let us say, dealing with car number n and this is dealing with car number n minus 1, then they have no correlation. So and that is why you can very easily do it. Now we have to also establish similar kind of strategy here. So when this instruction is one instruction, let us say instruction number n is in OF stage, I can deal with an instruction which is, let us say, instruction number p, and they should be completely independent. Okay. So that is what pipeline allow us to do. Now to do that, to ensure that they are completely independent, I have to have some kind of a sequencing element inserted in between, so that the data which gets computed in a particular stage is not passed without any synchronization to the next stage. The data should be passed only when the thing which was getting executed in this stage is done and the previous data has moved to the next stage, then only you should push the new data here. Otherwise, basically there will not be any correctness in your execution. All right. So similarly, you will have sequencing elements or flip flops in between these different stages, and so on. So these flip flops, you see that in this kind of scenarios, you will be sending a 32-bit instruction, you will be sending a basically PC which is again 32-bit and so on. So a single flip flop will not be sufficient. So for each of the wires you will need a sequencing element. All right. Okay. And that's and these sequencing elements or chain of flip flops or register files or registers are in between your different combinational logic, and when they allow the data to move to the next stage, they are done in a synchronized manner, and the synchronization is done by the clock. So whenever the clock says that okay, this is the moment you should pass the data to the next stage, so that this stage also does the same thing. So it pushes the old data to the next stage and the new data is pushed to this stage from the previous stage, and so on. All right. So you can think of these things as resistors or sequencing elements as resistors. So, as if you are basically transferring data from one resistor level to another resistor level. In between, you are manipulating your data through combinational logic, and that is why it is called resistor transfer logic. All right. And as you can intuitively tell that the clock frequency is determined by the slowest stage in your execution. So, basically in your processor there are 5 stages: instruction fetch. So, we will call the operand fetch stage interchangeably as decode stage as well, because this is much more easier to write. Then execute stage, then your memory stage, and then finally the register write back stage. So, so these are the letters we will try to use for denoting the different stages of our pipeline. So, this can be also denoted as with the letter F only: fetch stage, fetch, decode, execute, memory and write back. All right. Okay. So, so just to highlight what all we have discussed so far, we talked about how this pipeline can be implemented, and we also a very top level we have seen that okay, if we think of these different 5 stages of our processor, and if we can put some sequencing element in between, we can also introduce pipeline there. Now, before we look into the pipeline, basically the basic or ideal pipeline characteristics, I will just note down. So, for an ideal pipeline, so all the objects or all the basically here we can see all the cars has to go through all the stages. Similarly, all the, if we talk in terms of instruction, all the instructions should go through all the stages simultaneously. Basically all the stages. So, all objects or all cars or instruction go through same stages. So, for example, you can't say that okay, this instruction does not have an executor, it does not require execution unit, so I will just skip the execution stage. It is not allowed. The next very important point is, between the different stages there should not be any sharing of resources. Because if you share resources between stages, then they will not be any longer independent. The third part is the delays in each of the stages, they has to be same. Now, I know it may not, in our example we have seen that the delays are not same, but in that case also what we have done, we have forcefully made it same. We said that okay, different stages are taking different time, so basically we look at the maximum time, and according to that maximum time we said that okay, this is the delay each stage has to go through. So, once we take this call, then every stage has to go through the same amount of delay. All right, because if different stages go through different amount of delay, then again there will be this problem of piling up. So, one stage will take longer, one stage will take shorter time, and so on. So, the propagation delay through all the pipeline stages is equal. Now, the last thing is basically and the last one is basically the scheduling of a transaction which is happening in or which is going to enter in the pipeline is not affected by the transaction in other stages. So, basically scheduling all right. So these are the characteristics or properties of an ideal pipeline. Now, most of these characteristics or properties are kind of valid for most of the practical pipelines which we see, whether it's assembly line, car assembly line, or let us say the mess example we keep giving repeating about. But if you think about it, in a computer program, the instructions are generally dependent on each other. So, one instruction will have some kind of dependence, it might have some dependence. For example, let us say one variable is getting updated and in the next instruction the same variable is being used. So, there is dependency. It is not like two independent entity taking food from the the food counters, because they are completely independent. So, they are not at all dependent. Or let us say car assembly line. So, each of the cars are independent. So, there will not be a situation where the outcome of one car will be dependent on some other car. So, this kind of independence is or this kind of all this ideal behavior is available in most of the real life pipeline scenarios, but in case of computers the instructions are not always like that. Instructions are dependent by design, and that is why it becomes very important that this pipeline is implemented in the most appropriate manner, because there will be challenges because of these dependencies, and those challenges need to be dealt with appropriately, and that is why this pipelining part is so important. So, just to so from our discussion so far, what we have done, we have said that okay, we have these 5 stages of our processor, and since each of the stages are not simultaneously used, so once when one stage is getting used, the other stages are sitting idle, and we want to avoid that. That is why we said that okay, we will try to implement pipelining. Now, just like in a car assembly line, so when let us say some work on one car is getting done, in other stages other cars are getting built, and so on. Now, with this same concept, we said that okay, we will be designing our processor as a pipelined processor. So, the pipeline stages of our processor are let me write it down. So, as we said, like we will be denoting, so let me just write it down. So, this is our pipeline processor. The pipeline processor has 5 stages, as we have seen in detail each of the stages. So, we will denote these stages as fetch stage, then we have decode stage, then we have execute stage, memory stage, and write back stage. All right. Now, since these are pipeline, this is a pipeline processor. So, the advantage is that I can have in each of these stages different instructions. So, basically, for example, there can be a situation where instruction 1 is in write back stage, instruction 2 is in memory stage, instruction 3 is in execute, instruction 4 is in decode, and instruction 5 is in fetch. So, what essentially is happening here, I have 5 instructions. So, instruction 1, instruction 2, 3, 4 and 5. Now, let us say these are the clock cycles. So, let us say this is clock cycle 1, 2, 3, 4, 5, 6. So, instruction 1 in clock cycle 1 moves to fetch stage, clock cycle 2 it moves to decode stage, then execute stage, then memory stage, and then on clock cycle 5 it moves to write back stage. How about instruction 2? So, this is instruction 1. Instruction 2 starts its journey from clock cycle 2, because in clock cycle 1 instruction 1 was in fetch stage. Now, in clock cycle 2 instruction 1 has moved to decode stage. So, the fetch stage is empty, it is just waiting or is idle. So, in clock cycle 2 when fetch stage is empty, I can basically start fetching the instruction number 2. So, I will fetch it in clock cycle 2, then I will go ahead with decode, execute, memory and write back. Instruction 3, what will happen? As soon as after in instruction 3 this fetch unit becomes available. So, instruction 3 is fetched, decode, execute, memory, write back. Similarly, instruction 5 will fetch, decode, execute, memory and write. And instruction 6 fetch, decode, execute, memory, write back. So, this snapshot we are looking at this situation, right. You see that instruction 1 is in write back, instruction 2 is in memory, instruction 3 is in execution, instruction 4 is in decode, instruction 5 is in fetch stage. So, you see that because of this pipelining mechanism, now we can execute multiple instruction simultaneously. Okay. So, multiple instructions are at different stages of the pipeline and they are getting executed as we in every clock cycle some part of the instruction is getting executed. And basically every time the clock comes, the instruction moves to the next stage and this is what is pipelining, and this is ensured by putting some sequencing element between these different stages. So, all the communication, so you remember that each of these different modules have their own input and output. Now, all this input and output which is going from one stage to another goes through this flip flops or sequencing elements, so that the data can move from this stage to next stage only when the clock signal comes, because you want to make sure that the appropriate data moves to the next stage, and you work on that data to evaluate the appropriate outcome. All right. So, this is what is pipelining, and I have also basically, without giving you much detail, I have also shown how these pipeline diagrams we will be drawing in the class. All right. So, this is how typically we will show the different execution stages of our program. So, we will have different instructions, we will have clock cycles, and then basically we will denote at what clock cycle in what stage this particular instruction is. So, this is one way of representing. The other way of representing, which the book also highlights or book follows, is basically you just swap your rows and columns. So, basically here you write down let us say the different stages of the pipeline: fetch, decode, execute, memory, and write back. And here you will have clock cycles, and here you will write down the instruction. For example, instruction 1 first is in fetch stage, then it will be written decode here. So, the instruction 1 in clock cycle 2 will move to this decode stage, and 3 and so on. So, this is just a different way of representing. So, if you want, I can in a very small place I can show it. So, basically we have these different stages of the memory: fetch, decode, execute, memory, and write back. So, we have these cycles, clock cycles. So, 1, 2, 3, 4, 5 and so on. So, in clock cycle 1, instruction 1, let us say I will not write instruction, I will just write maybe 1. So, it denotes instruction 1 is in fetch stage. In clock cycle 2, instruction 1 is in decode stage. In clock cycle 3, instruction 1 is in execute stage, and it is in memory stage in instruction 4, clock cycle 4, and then in clock cycle 5 it is in write back stage. The instruction number 2 is in fetch stage in clock cycle 1. So, this is 2, the instruction number 2. All right. Then it moves to decode stage in cycle number 3 and so on. Similarly, you can write down 3 here and so on. So, this is another way of representing this thing, but we will primarily sticking to this representation. All right. So, the advantage of the pipelining is very intuitive. We keep the different components or different parts of the data path busy all the time. So, basically we keep all the parts of the data path busy all the time. and if we assume that all the stages take the same amount of time, or basically they take equal amount of time, all the 5 stages, then it is very intuitive that without any pipelining, uh, uh, like one instruction, if it took t seconds without pipelining, so let us say an instruction takes t seconds to execute without pipelining. Now it is very intuitive that with pipelining the instruction will take t by 5 seconds, right, because you will be getting so earlier, let us say this was the whole data path. So you give an instruction, it gets executed, it takes t seconds. So if you get an executed instruction every t second. Now your this data path remains same, but what you have done, you have broke that data path into 5 stages, and each of these stages are taking t by 5 time. So total time is still t. So the total time is still t, but here, though each stage is taking t by 5 seconds, I will have instruction 1, I will have 5 instructions at basically simultaneously in the data path. So so basically this may be instruction 1, this may be 2, 3, 4 and 5, and like every t by 5 second I will get a new instruction coming out of this, right, because like while instruction 1 entered here and came out after t seconds, but instruction 2 will be available after t by 5 seconds, instruction 3 will be available after additional t by 5 seconds, and so on. So every t by 5 seconds I will get an outcome. Every t by 5 seconds I will have an instruction executed. So this is a huge advantage. So if everything goes well, then my performance will become 5 times, like right. So yeah, now to implement this pipeline, as we said, like we have to introduce latches, basically flip flops between the different stages, and we have to make sure those flip flops are appropriately inserted, and the stages are also divided in such a way that they take more or less same time. So yeah, this is what we will be looking at next. Okay, so if we just draw this block diagram of the pipeline again, I will try to quickly make this point. So these are our 5 stages. So fetch, decode, execute, memory and write back. Now we have already said that we have to have flip flops or sequencing elements in between these stages, so that any data movement happens through this flip flop. So I am not saying that there will be a single flip flop, there will be basically you can think of registers which will only allow the data to move from this stage to this stage when the clock edge comes. So these sequencing elements will be ensuring that. All right. Now, so the data movement happens from here to here through this register file, this flip flops or registers. Now we also have briefly talked about that all these sequencing elements will be controlled by the same clock, right. So, this is our clock. Now, let us say each of these stages, let us say the fetch stage take a time which is denoted by Tm, the time required to perform the fetch operation is Tm. Similarly, the decode stage or basically the this operand fetch stage takes, let us say, time, just for simplicity I am denoting it by d, t subscript d. The execution phase takes something like tx, and memory phase takes time as okay. So, we can't, oh, this should be m, this should be f, fetch, and this is memory, and this is write back. All right. So, now if the clock we are selecting has a period of Tc, then from our previous discussion we can intuitively say that Tc, the time period of the clock, should be greater than the max of your Tf, Td, Tx, Tm and Tw. So, whichever is taking maximum amount of time, and that should determine our clock frequency. And some of you might have heard the term called critical path. So, in your digital design you will be hearing this term critical path very frequently. So, it denotes the path which takes the maximum amount of time. So, here you can think of whichever of these modules take the maximum amount of time, that will determine the clock frequency. Now, if you want to run your processor faster, then you have to make sure that the path which is taking most amount of time, you improve that, so that it starts taking less amount of time, and if you can do that, then basically you can run your processor faster. Okay. So, I hope this makes sense. So, this is very, very important. Now, intuitively, if you just remember the different modules we have looked at. So, we have looked at the actual implementation of all these modules. Now, we have seen that the fetch unit is pretty simple, there is not much work done. The operand unit is pretty beefy, because here you need to calculate the immediate values, you need to read the registers, and basically you need to also find out the branch outcome, if I remember correctly. So, basically offset values related to the branch. So, that also needs to be calculated. So, there are multiple things you are doing here, and register file read is also depending on how many basically read ports are there, etc. You might need more time. So, basically this this unit is pretty complex, and in many implementation it has been observed that this this stage takes significant amount of time, and many a times basically this can be a bottleneck. Especially we will see that when okay, we will not see it in this course, but let us say if you want to do out of order execution, etc., that time the amount of work you need to do in this decode stage becomes much more. You have to also see the availability of your operands, etc., that also is done in this decode stage itself. The execution stage we have seen. The other very critical unit is this memory unit. So, because you need to read memory, and if the data is not available in your let us say in your registers, basically you need to read it from main memory, then this takes significant amount of time. So, this can be also your critical path. So, and then the write back. So basically depending on which of these stages are taking maximum amount of time, your critical path length varies, and accordingly you have to look at your design, you have to figure out your clock frequency, etc. All right. So, we will pause here, and we will continue our further discussion on pipeline from here in our next video segment.